Hey everybody, this is Mrs. Rajewski. Welcome back. Today we are going to talk about something called implicit differentiation. But before we get started, I want you to get your brains kind of warmed up. So I want you to try this warm up. So, this should say exercises 1 through 2. So let's change that. It used to be 1 through 3, but I think I make my point with problems 1 through 2. So let's go ahead and isolate this y prime in each of these equations. So for problem number 1, I'll do that one in the black pen. We've got x squared times y prime minus 2xy equals 4x minus y. So I just want to get the y prime alone. Well, that's easy. I'm going to add 2xy over to the other side. Not too shabby. So I've got x squared y prime is equal to 4x minus y plus 2xy. Okay, now the only thing that's stopping y prime from being alone is this x squared, and it's multiplying itself. So we are going to divide both sides by x squared. So I get y prime is equal to 4x minus y plus 2xy all divided by x squared. And you could try simplifying this, I guess, by splitting it up into separate fractions, but for all intents and purposes, we are done here. Now, this wasn't too terribly difficult to get the variable y prime isolated. It wasn't so bad. Let's check it out over here. So here I've got y prime that's multiplied times the sine of x, and I also have y prime multiplied by this x over here. So kind of like my plan is to get all my y primes onto one side and everything else onto the other. So I'm actually going to use the opposite operation to move this xy prime over to this side. So these guys will cancel out. And I'm going to move this negative x cosine x over to the other side of the equal sign. So I'm going to add that to move it across the equal sign. Okay, so what I have now is y prime sine minus xy prime. These subtract to make 0. And we've got y plus x times the cosine of x. Well, y prime is not alone. I've got 2 of them. When you find yourself in this situation, your best bet is to factor. So let's go ahead and factor out these y primes. So since that's what each of these terms have in common, we'll factor it out. This is going to leave me with the sine of x minus x inside my factoring parentheses. And we are nearly done here because we just have one step left to get this y prime alone. Since y prime is multiplying itself times this quantity, we'll use the opposite operation, which is division, to move this quantity, the sine of x minus x, all over to the other side. Now, just so you know, this is the x that's in the argument, and the whole sine of x is being subtracted by x, because you might be like, well, why is that just not sine of 0? Nope, no big deal. And here we go. Now, these equations weren't terribly difficult for us to isolate the variable y, or y prime, to be precise. But sometimes equations are really, really difficult to isolate for one particular variable. And so that's where implicit differentiation comes in. So let's first talk about equations that we're used to, right? So you're used to seeing equations that are solved for y, like y equals x squared and y equals the sine of x. These are explicit equations. When we know x, we can calculate y directly. Like there's no extra calculations we have to do. But these other equations over here, like x squared plus y squared equals 2xy and 2y minus 4x equals the sine of xy, we're not solved for y. So knowing a particular value of x isn't going to easily help us figure out what the output y is. It doesn't lead directly to it. And so when you don't have it leading directly to it, so essentially you're not solved for y, you have an implicit equation. That's the difference between these equations. Do you see that? I bet you do. So far, we've been working with derivatives that are written explicitly. So we take derivatives of explicit equations. But in order to take a derivative, we don't have to have explicit equations. Instead, now I'm going to show you how, if you have an implicit equation, how you be able to calculate the derivative. It's not too bad. So let's take, for example, normally we take the derivative, the variables match up. I'm taking the derivative with respect to x. I've gotten x, so the derivative with respect to x is 2x. Easy peasy. But what if we're asked to find the derivative with respect to x of y squared? Now, I don't have an x here. So how can I take the derivative with respect to x if there doesn't exist this x? So that's what implicit differentiation is going to help us to do. So to take the derivative with respect to x, even when we don't have an x. So let's take, for example, this problem, okay? We could actually think of it as taking the derivative with respect to y and then taking the derivative of y with respect to x. So I just want to point out here that conceivably we could be canceling out these dy's, and I wouldn't have actually changed the value of the original problem, right? I still have a d dx and y squared, d dx and a y squared. But it's another way of us like thinking about the setup of the problem. And then we can switch the order so that I've got d dy, the derivative with respect to y, of y squared, and then the derivative of y with respect to x. See, I just flip-flopped these guys. Okay? Still haven't changed the value of anything. Now I'm taking the derivative with respect to y of y squared. And you could say, well, that's just 2y, right? So that's this piece here. So what's left over? Well, it's dy dx. And that's cool. That's how we do implicit differentiation. That's it. You just end up with this little leftover dy dx. It tells us that, hey, we took the derivative, but there wasn't an x there. Now you might think, this is crazy. But you know what's crazier? The fact that you've been doing this all along. I'm not asking you to do anything crazy. See, every single time that you were taking the derivative of an explicit function, like y is equal to 3x plus 4, didn't we write, oh, the derivative of y with respect to x is equal to 3? We always took the derivative of y and then called it dy dx. That's the same thing we just did here. We took the derivative of y and then we called it dy dx. So you have actually been doing this the whole time. It just tells us you took the derivative of y. Easy, huh? So when are you going to use implicit differentiation, throwing in this extra dy dx, or telling the world that you took the derivative of y and not the derivative of x? When do we do that? Well, we do that when it's very difficult or impossible to isolate the y value. It's not impossible to isolate y in this equation here, but it's not pleasant, and you're going to be working with rational exponents. It might not bring you joy while you're doing this. Or how about if I asked you to go ahead and get y alone from this equation? Ay, Dios mío. You're not going to be happy. So my suggestion is, use implicit differentiation, because sometimes it's really, really difficult to isolate your variable y. So basically, like I already said, the key is to remember that the derivative of y is y prime or dy dx. I'm most of the time going to write dy dx. And you're just going to make sure you're using the chain rule, all those other rules, the power rule. You're going to still use them all. Nothing has really changed. It's just you're going to have two variables in your equation instead of just one. Well, really, you always had to, but we always just wrote the derivative of y as dy dx, and we're going to continue that. So here we go. Example number 1. So let's take the derivative with respect to x of y cubed. Okay, well, I'm going to take the derivative of y cubed, which is 3y squared, and then I'm going to multiply by dy dx, because the derivative of y is dy dx, kind of like your chain rule. That's the inside function. Okay, let's continue over here. This next problem, the derivative with respect to x of 1 divided by y squared. Well, honestly, I would write 1 divided by y squared with a negative exponent. So I would say this problem is really y to the negative 2. Find the derivative of y to the negative 2 power. And that's easy to calculate. I'm going to multiply by negative 2 in the front. I'm going to subtract 1 from my exponent, so that'll be negative 3. And then the derivative of y is dy dx. And if you really want to, you could rewrite this so it says negative 2 divided by y cubed dy dx. And that's up to you. And last one here. Ooh, this is the product rule. I love that. So we're going to take the derivative of this product. So here's our first factor and our second factor, right? To do the product rule, it's 1 d2 plus 2 d1, the product rule. It's so much fun. So 1 d2. So we're going to take the derivative of y squared, which is 2y dy dx. 1 d2 plus 2 d1. Now, if I wrote the derivative of x with respect to x, that'd be like dx dx, which is 1. So we don't really write that. Do you see what I mean? And we can tidy this up just a tad bit. I've got x squared times 2y, so that's going to be 2x squared y dy dx. And then y squared times 2x is 2x y squared. I like to keep them in the proper order. And there we go. So the only difference is when you take a derivative of a y, you're going to slap that dy dx right on there. Not too bad. So let's try example number 2. We're supposed to find the dy dx if we have this whole equation. So those last problems were expressions. Now we got equations because we have an equal sign. That's all right. So my plan here is just to take the derivative of each term, and then I'm going to solve it for dy dx. That's going to give me my slope. All right. So my first term, x cubed, that's going to give me 3x squared. My second term, this has the y in it, so I'm going to multiply 4 to the front. That's going to give me 28. Subtract 1 from my exponent, just like usual. But because this is a y, the derivative of y is dy dx. It's like the chain rule. My inside function was a y, not an x. The derivative of y is dy dx. And now, the derivative of a constant, well, that's 0. Fancy. This doesn't just ask me to take the derivative. It says to find dy dx. So that's why I said we're going to solve for dy dx, kind of like in our warm-up. We're going to get dy dx alone. So I'm going to subtract 3x squared to the other side. And I get 28y cubed dy dx equals negative 3x squared. Now, the only thing stopping dy dx from being alone is this 28y cubed. So I'm going to divide both sides of my equation by 28y cubed. And we get dy dx is equal to negative 3x squared divided by 28y cubed. Done and done. Let's try another one. This one is a little bit more intense. So let's try it out. Here, the derivative of x, well, that's not so bad. That's just 1. All right, I can live with that. Ooh, xy. This is a product, so we have to use the product rule. So that's 1d2. The derivative of y is dy dx. So 1d2 plus 2 d1. Now notice that I did not use a dy dx here. That's because I didn't take the derivative of y. 1d2 plus 2d1. You take the derivative of the first term, not the second term on that second half. So that's why I didn't use it there. And then, plus y, I have to take the derivative of this y. That's just going to be dy dx. Equals, the sine of 2x. That's a chain rule problem. The derivative of sine is cosine. Keep the inside the same, and then multiply by the derivative of the inside. Chain rule. Actually, I'll admit I kind of love the chain rule. All right, so the directions are the same though. We're still going to find dy dx, so I'm going to move everything that does not have a dy dx over to the other side of the equal sign. So I'm going to subtract 1. And I'm going to subtract y. And this leaves me with x dy dx plus dy dx is equal to, let's say, 2 cosine of 2x minus 1 minus y. And in this situation, I would go ahead and factor out that dy dx. If we factor it out, what's left will give me x plus, well, if I factor out the dy dx here, what's left? 1, because, it's the opposite of the distributive property, so yeah. And finally, we've got one last step to get dy dx alone. It's getting multiplied by x plus 1, so we are going to divide by the quantity x plus 1. And let's move this guy over a bit. There we go. And my final answer is dy dx is equal to 2 times the cosine of 2x minus 1 minus y, all divided by the quantity x plus 1. Final answer. Well, that was a doozy. But hopefully you're seeing that all of our same rules still apply here for derivatives. Just if you take the derivative of a y, it's dy dx, the chain rule. So how about you guys try this one? Yeah, I know. You don't have your whiteboards. That's all right. You do have your notes, however. So go ahead and pause the video and see if you can solve it the same as I do. Did you pause it? Go ahead and pause it. All right, so here's how I would solve this. You use the power rule. So I have 3x squared plus 3y squared. But when you take the derivative of y, you get dy dx. Then on the other side of the equal sign, I've got 18xy. Now this is a product, so I'm going to have to use the product rule. 1d2 plus 2d1. The product rule is so much fun. Now we have to find dy dx, so I've got to get all the dy dx's onto the same side. I think I'm going to move them to the right. I usually go to the left, but I like to keep my leading coefficient positive. It's up to you, whatever you like to do. I'm feeling crazy today, so let's go for it. Minus 18y to the other side. And let's go ahead and subtract 3y squared dy dx. So these make 0 and these make 0. It's going to leave us with 3x squared minus 18y is equal to 18x dy dx minus 3y squared dy dx. Okay, well, my dy dx's, they have that in common, so we can factor that out. They're also both divisible by 3. I mean, we could factor that out as well. I'll hold on to it for right now. Let's see what we got. Dy dx times the quantity 18x minus 3y squared. I'm going to factor this one. Somebody stop me. I'm a factoring fool. So that will give me x squared minus 6y. Divide both sides by, I'm going to put it in factored form. Hopefully I won't take you to crazy town with that one. Again, I'm going to factor it out. So that's going to be divide that on both sides. Hopefully you can see why I'm doing that. I just want to be able to cancel those 3's out. You guys feel me on that one? Just want to have it be as simple as it can be. So my 3 is reduced to 1, and I got x squared minus 6y, all divided by the quantity 6x minus y squared is equal to dy dx. And just in case I went through that too quickly, 18x minus 3y squared, they're both divisible by 3, so I just factored it when I divided it over to the other side. So hopefully that wasn't too fast for you. Well, that was like the worst circle ever. No, yeah, I'm not trying to make it a circle this time. I was just trying to circle my answer. You know what I mean. Okay, so how about this one? Let's try it. Why not? Let's see what happens. Here we go. So pause it and try it yourself first, and then see what you don't understand. See, like, you can actually learn a lot from making mistakes. So if you start going through this and then you realize you're stuck or you're feeling like this isn't quite right, then go ahead and unpause the video, and then maybe you'll get that little hint that's necessary to be able to push yourself forward through the problem. Okay, so really do try it on your own. Here we go. So the derivative of x squared is 2x. Minus 7xy, this is a product, so I'm going to have to use the product rule. 1 d2 plus 2 d1. The product rule is so much fun. So I decided to put my minus sign on the outside and then have the whole product be the positive 7xy, just so that I wouldn't forget that I need to distribute that negative to both terms. That's up to you how you want to do that. Plus 2y dy dx is equal to 2. Okay, so don't forget, even with the 2y, I have to multiply by the dy dx because it's a chain rule. The function inside is a y, and the derivative of y is dy dx. All right, so little distribution. You may have treated that as a negative 7xy, and so you already had the negative in here. That's cool. So I got 2x minus 7x dy dx minus 7y plus 2y dy dx is equal to 2. I'm going to get all my dy dx's on one side. Luckily, they're on one side, but I'm going to have to move everything else away. So subtract 2x to the other side. That makes 0. So I'm going to add 7y to the other side. And that makes 0. And then all that's left here are dy dx's. So let's factor them out. This term has a dy dx. This term has a dy dx. The other terms canceled out. So I've got dy dx times the quantity negative 7x positive 2y equals 2 minus 2x plus 7y. Oh, we are one step away. Here we go. Negative 7x plus 2y. I'm going to divide it to the other side, leaving me with a lovely dy dx all by itself. And I've got 2 minus 2x plus 7y, all divided by negative 7x plus 2y. Fantastic. All right, my friends, we only have one left to do. Here we go. And this is example number 3. All right, here we go. Here we go. So, example number 3, we're going to find the gradient of the tangent to x squared minus y squared equals 9 at the point where x is equal to negative 5. All right. So just like last time, we're going to take the derivative. Now, here's the deal. To find the gradient, that's a fancy way of asking you to find the slope or the derivative, okay? And the tangent line, the tangent is the slope that we normally find, okay? So here we go. X squared, the derivative of x squared is 2x. Derivative of negative y squared is negative 2y dy dx. The derivative of 9 is 0. Let's get dy dx alone. I'm going to subtract 2x to the other side. Okay, so once we've got almost our dy dx alone, let's divide both sides by negative 2y. Well, negative 2 divided by negative 2 is 1, so I get x divided by y. This is great. So this is kind of an interesting slope situation. This is the slope generating equation for this function, x squared minus y squared equals 9. And they want to know what's the slope when x is equal to 5. Well, in order to find the slope, that's our derivative, I need to know the x and the y value. They've only given us the x value, but this isn't actually very difficult for us to calculate. In order to find y, we're just going to substitute this x value into our function, and we should be able to solve it and figure out what y is equal to. So let's go for it. I'm going to substitute in 5 for my x in the original equation. You can't really substitute the derivative equation yet because you don't have a y and you don't know what the slope is. That's the whole point of the question. So I've got 25 minus y squared is equal to 9. Well, I'm going to subtract 25 to the other side. That's going to give me negative 16, which I'll divide both sides by that little pesky negative 1. And I get y squared is equal to 16. Ooh. When you take the square root on both sides to get rid of that square, you'll get that y is equal to plus or minus 4. And I will tell you that I thought, oh, this is interesting. There are 2 points where x is equal to 5. It's either going to have a y value of positive 4 or a y value of negative 4. So I'm going to come up with 2 slopes. So when you're at the point 5, positive 4, the slope dy dx is going to equal 5 divided by 4 because your slope is x divided by y. But when you're at the point 5, negative 4, your slope, the dy dx, is going to be 5 divided by negative 4. Like going in the opposite direction. And I will tell you that this caused me some curiosity. Of course, you know what I did next? To Desmos. So that's what I did. So let's go to Desmos real quick. And I graphed it. And then I was looking and I saw here's at the 0.54, here's at the 0.5, negative 4. And the slope does look similar, just flipped. And that's exactly what's happening here. Since we're increasing in this direction, we've got that positive slope. And as we move in this direction, we're decreasing, and this is our negative slope. So it actually does kind of make sense that I have this kind of interesting result for the slopes. Anyways, I probably should have taken a snapshot of that. But anyways, there we go. I think we should probably try this as well. Why not? So pretty similar problem. We get 2x plus 2y dy dx is equal to 0. I'm going to solve it for dy dx. This one's nice because they've already given us the point. Divide by 2y. And I get dy dx is equal to, looks like negative x over y. That's nice. Okay. So find the lines. So this isn't just what's the slope. They want us to know what's the lines that are tangent and normal to the circle at the indicated point. All right. So if this is our slope generating equation, at the point 0, 3, the tangent is going to be where the slope is equal to negative x divided by y. So negative x divided by y. Well, that's just 0. Interesting. So if I was going to write that as an equation, I would have y minus the y value from our point is equal to our slope times x minus the x value from our point. And I get y minus 3 equals 0. Y is equal to 3. This is my tangent line. Now the normal line is the opposite reciprocal slope. So we use the symbol, it's like this upside down T, that's a perpendicular line. That's what a normal line is, it's perpendicular. So we say the normal slope is the opposite sign and reciprocal. Oh my goodness, Mrs. Rajewski. Let's do it this way. The opposite of the reciprocal, like this. And this is crazy, right? Because now we're dividing by 0. Like, what kind of crazy world is this? This is undefined. And undefineds only happen when we have these x equals lines. So what kind of line is it? It's x equals 0. These are undefined lines. Remember, if you're like graphing this, this is a line that goes straight up and down. That's the undefined slope. Okay, this is obviously not at x equals 0 because it's a little bit less easy to show you what that looks like. But there you have it. We could try graphing that too. X squared plus y squared equals 9. It's going to be pretty similar to what we had before. And we're looking at the point 0, 3. And check it out. If we have the line y equals 3, that is the normal line. That's the slope at that point. If we have the equation x equals 0, that's this line that goes straight up and down through. That is the perpendicular slope. Isn't that fantastic? I'm pretty excited about it myself. So there you have it, guys. Implicit differentiation, a couple of different ways. Please go onto My Lab in Mastering and do the day 9 homework. And if you're doing the textbook assignment, then this is the textbook assignment down below. I hope you guys are doing well. I miss you lots, and I'll see you next time. Bye.